talking about computing limits algebraically or analytically, and this is going to take away a little bit of the, I don't know, ambiguity we had whenever we're doing the limits numerically. So the first few things that you need to know is that limits are linear, so meaning that the limit as x goes to some value c of f of x plus g of x is going to be equal to the sum of the limits. Same thing, you can pull constant in and out of the limit. So the limit as x goes to c, those two together are the linearity, and say a constant, let's say alpha, is going to be equal to alpha. So you can pull out constants. Now you have products. Products work well with limits as well. So limit of the product is the product of the limits. So limit as x goes to c, and then f of x times g of x is equal to the limit as x goes to c of f of x times the limit as x goes to c of g of x. And this will automatically imply, for example, that the limit of a power is the power of the limit. So you can move powers in and out of the limits, if you will. Positive powers, I should say. And then we got to be careful also with when you're doing a division. So a quotient of a limit is the limit of a quotient, not the quotient of limit. The limit of a quotient is the quotient of the limits, and you gotta be somewhat careful. What would be, if without me saying it, what do you think would be the problem of writing it this way? When do we get a problem? The problem is if this happens to be 0, so we're gonna restrict it to the case when the limits are in the denominators are not equal to 0. Okay, so all that is in your notes, and the use for it is that this allows us to compute limits that, or the option. I'm gonna be a little bit less precise on this one, just because I don't want to go in too much detail, but it's going to allow us to compute the limits whenever we can do it by direct evaluation. So we can evaluate the function at a specific at the in this case limit 3, and we get a value back. That's going to be our limit. What does that mean? So if I have, for example, a polynomial where you don't have any problems just plugging in your value of x, in that case, if you follow the rules I gave you that I wrote above, then this would break out, and I'm going to do it in quite a summarized way, but it would just break down to just being the limit as x goes to 3 of x squared plus 3 limit as x goes to 3 of x. So basically just moving the limit inside of every operation, and the limit as x goes to 3 of 1, and the only thing we would have to have established that is true is that the limit as x goes to 3 of x is just 3, and then you can plug that in, and then the limit of a constant is a constant, and with that, if we establish that, then we would have that this limit is just the evaluation of the function at 3, and that for algebraic functions that is going to be true. So if I give you something that just says compute the limit and you plug in the value, in this case, by the way, 9 and 9 is 18, so 19. If you get a value back, you don't get zeros in the denominator, you don't get things that are undefined, for algebraically, for example, trigonometric functions that would be undefined. If you don't get any of that, then your limit is the number you're getting. So that's why whenever I'm gonna give you a limit, I say the first thing you do is just plug in the number I gave you, or the number here. Just plug it in, and see if you get a value. If you get a value, then that will very likely be your limit. In fact, with the function that we use in this course, that is going to be your limit. With that, then that's your first strategy, your first step in your strategy to compute limits. All right, so then there's a very important theorem that we're going to be using. We don't prove it, but it's a very important theorem. So if a function is equal, or g, say, is equal to f, at all points in an open interval I that contains C, with possibly the exception of the point C. What do I mean? So the functions are equal at all points with the possible exception of that C. Everywhere else on that interval, they're the same. Then limit as x goes to C of f of x is the same as limit as x goes to C of g of x. Yeah, open interval. I did say open interval. I was saying, oh no, I forgot open. No, it's open. All right, so what does that mean? So if I have, say, the case when you had the function, remember we did the first day of class, y equals x squared minus 4 over x minus 2. And that was that one that was a line, the line x plus 2, and with the exception of the point 2, where it had an open hole there. These two functions, this is equal to, remember we factored because we had 0 over 0 at x equals 2, and we said WTF, we want to factor, as you all remember. Then we factor and we got that this was equal to x plus 2 when x is not equal to x equals to 2. So this is the situation I'm describing here. So these two functions, you could call this one f of x, and you could call this g of x. They're equal at all points with the exception of just one value, x equals to 2. That's going to be our c. Then what that tells us is that the limit as x goes to, what the theorem tells us, that the limit as x goes to 2 of this function x squared minus 4 over x minus 2 is equal to the limit as x goes to 2 of x plus 2. And now notice that this is one of those where I can just plug in the value. The 2 went away somewhere. I can just plug in the value of 2. If I plug x equals to 2, this is 2 plus 2 equals 4. So this limit by the previous discussion is defined. So you see, I don't have to do my limit numerically. I can compute my limits when I have a 0 over 0. That it would be the case over here. I can do them by factoring. So in your book, you have a table that gives you a strategy, and the strategy is if you have a 0 over 0, then find a function that matches, that means factor out and cancel things as needed, and then try to plug in the value. If you get a number, then that's going to be your limit. They call the last step. They say, lastly, we apply the limit laws, but really they're just plugging in a number. All right, so let's go ahead and do a bunch of examples and see how this goes. All right, so let's do this one as our first example. So let's say that we don't even know what we're doing here. No, we do know what we're doing here, but we don't know what the limit will be. That's what I meant. So we first start by evaluating the function that we have at x equals to -2. Where is that -2 coming from? That -2 is here. So I use that value, and I evaluate it. I get -2 squared. By the way, use parentheses when you're evaluating negative numbers in particular. In general, you should use your parentheses, but if you're going to use negative numbers, please use your parentheses, because people mess up, and then without the parentheses they just put -2 squared, and then they square only the 2 and forget that the negative was supposed to be included, but they didn't write it. So that is a source of issues. So when you're evaluating, just use more parentheses. More parentheses is better than less parentheses. So I always prefer that. So -2 squared is 4, minus 4 is 0. I just evaluate that, and then here I get -2 squared is +4. +4 plus 3 times -2. 3 times -2 is -6. So +4 plus -6 is -2. Oh, my problem was wrong. Well, otherwise, never mind. I'll address both situations. I wanted the plus, so I get a 0 in the denominator. I messed up my numbers when I did it in my head here a second ago. But this is going to be a 0 over 0, which is a U1 factor situation. So 1 to factor, because I got 0 over 0. I already explained it in class, so I'm saying it nonchalantly now. So there. But the one thing is that if I would have left that -2, by the way, and I would have ended up having a -4 in the denominator, that limit is 0, and you're done. So if I would have had the 0 over -4 as I had done, then your limit is 0, and you're done. Then you don't have to do more. But of course, I want to explain to you the one that is useful for class, not the mistake. However, you just witnessed that those mistakes, I do make those mistakes once in a while, and if you get very lucky and I make the mistake when I'm writing your exam, then you have a free problem. So always evaluate before you start, okay? Those are factoring and wasting your time, and then realize, oh, he made a mistake. And it has happened before, by the way, because I just do them in my head and I write them, and then I don't check them, which is not something I should be admitting on video, but it's true. That's what I do, and I should learn from my mistakes, but I don't. Man, why am I beating myself up like that? Anyways, now you know. So +2, so I'm going to factor this is going to be x plus 2, x plus 1, because that's going to multiply to 2 and then adding up to 3 as you need, and better be, because I need to cancel that x plus 2 out. Now remember that in general you cannot just cancel them out, because that is only true whenever x is not equal to -2, because whenever you have -2 you have 0 divided by 0. That's what we established already. But in the limit we are allowed to consider the function that matches our original function at every possible point, with the exception perhaps of x equals to -2. The function x minus 2 over x plus 1, which is what I obtained here, matches my original function at every point. I keep clicking the eraser button. So this function and this function, so these two functions match at every single point, with the exception of x equals to -2. So on any open interval that includes -2, those two functions match. So the limit that I have here is going to be equal to the limit here. That's why I'm allowed to do the quote-unquote cancellation. I'm using the theorem that I just described. It's not that you can always just cancel it and ignore whenever you have 0 over 0. Only if you're computing the limits, because that theorem allows you to do that. And now we can just plug it in, because now we evaluate this limit by the properties of limits, where I can separate the limit of the numerator divided by the limit of the denominator, because the limit of the denominator is no longer 0, something that I couldn't do before because the limit in the denominator was 0. Now it's not, so I can just plug it in as I said, but really I will go with the book. You are using the limit laws. So now you do -2 minus 2 is -4, divided by -2 plus 1, -1, which is +4, and that gives you your limit. So the function does not take the value of 4. So it's not true that if f of x corresponds to the original function, x squared minus 4 over x squared plus 3x plus 2, it is not true that this does not imply that f at -2 is equal to 4. That, in fact, is not true. I'm going to put a big X. That's not true. But in the limit sense, so what the limit is telling us is you don't quite get that value, but the function gets arbitrarily close. You can get as close as you want to that value of 4. So when we did our analysis, whenever we're talking about the instantaneous velocity, so the function that you were evaluating had 0 in the numerator, 0 in the denominator. It's not that that function of the average velocity is taking the value of the instantaneous velocity, but if you define the instantaneous velocity as the limit of the average velocity, then the instantaneous velocity takes that value. So this limit is like your instantaneous velocity, but doesn't mean that the original function is taking that value. It just tells you that in the limit, so in this case, limit as x goes to -2 of f of x, that is going to be equal to 4, not the function itself. So there is the distinction. All right, so I skipped one exercise, well, two actually. One was supposed to just be practicing the notes. So if you're following the lecture notes from class, the problem that has a 2 and is the limit as x goes to 6 of x squared minus 8x plus 12, that one is the one that I normally assign as an exercise in class, and the answer is 4. I had to do it quickly, so please go ahead and check your knowledge on that one. Check that you're understanding. Take it as a checkpoint in the video, so pause and go ahead and solve it. Then the next one is example or exercise 2.14 in the notes. By the way, it also in the notes it'll also tell you to go to problems 2 to 5 in the worksheet and make sure that you can get those done. So it's a good time to practice as well. You can pause the video, make sure you're getting it. So the next problem is one from the book. I'm going to skip that one. I'm going to leave that one as practice, and I'm going to do the next one in our notes, which would have been the one I would have done as practice in class. So I'm just swapping them. I want to solve the one that I would have done as practice right now. So let's go ahead and work on that one. And so whenever you have a square root, again, your first step, you're going to evaluate. Oh, I have to change to the writing tool. You're going to evaluate at x equals to 6. Again, same strategy. So you evaluate there, and here's going to be the square root of 6 plus 8. Plug in x equals to 6. And then 6 minus 6. And as we had, the form is 0 over 0, and you say we want to factor. But I mean, technically you could factor this one, but that's, you'd have to factor this. So not that great. So what we're gonna do is a better alternative. We're gonna multiply times the conjugate. So you have square roots in the numerator. Remember when you did this in college algebra and you never understood why you had to multiply times the conjugate. So when you have minus, you change it into plus when you have radicals or square roots in particular. And the reason for it is because that then gives you the difference of squares. So you multiply and divide by it, and at x equals to 6, these are not zeros. You see you get square root of 14 plus square root of 14. Those are both positive numbers, so this is not zeros. You're doing two numbers divided by each other. You're multiplying times 1, and whatever you multiply times 1, you get the same thing back. So you're not really affecting your limit at all. And again, you're looking for a function that matches your original function, perhaps not at x equals to 6, but that you can actually evaluate your limit at. And so this one is a good candidate. You're multiplying times 1 in a clever way, if you will. And then you have to remember, though, so let me use colors here. So if you call this guy A and this guy B and this guy A and this guy B, whoa, not that. Boomer. I'm not a boomer. Nothing wrong with it either. What you have is A minus B times A plus B, which, if you remember, that is a difference of squares. So when you multiply this, remember when you're multiplying fractions, you multiply numerator times numerator, denominator times denominator. So that simply becomes, he says, becomes a squared, which is going to be square root of x plus 8. You can FOIL it out and you'll see the middle terms will cancel out. No need to do it. But if you don't believe me, I don't blame you. But go ahead and you can FOIL it out. You're going to get the same thing here. I already told you what rule we're using, or what, I mean. Yeah, rule. Let's call it that. Why not? We're afraid of calling things rules. And you say, okay, so you grabbed something that was quite lovely. I mean, just this part. And even though I didn't know how to work with it, it was not absolutely terrible as what you have right there. However, you can then grab this and turn it into an x plus 8. And then a minus 14. Whoa. And now it's going to start looking a little bit better. And copy that denominator, which is still a bit annoying, but not such a big deal anymore, because things will cancel. And I'm going to skip one step. I'm sorry, I will. And it's plus 8 minus 14. That's minus 6. I know, you should not do that. But it's YouTube, so you can pause it and write the line that I erased and then write the new line. So yeah, there. No, it's not justified, but I'll do it. Now, in the limit, remember that I'm allowed to cancel because I found a function that equals my original function at perhaps every point, with the exception of x equals 6, because by canceling that factor of 0 over 0 here, the functions don't match at 6. This function that is left over does give me a value at x equals 6. My original didn't. But that allows me then to compute the limit, because I can just say this is the limit as x goes to 6 of 1 over the root of x plus 8, the root of, well, evil, no, I'm kidding, plus the square root of 14. So you can just plug x equals to 6 now, and that gives you 1 over, and an equal sign would be very, very nice there. By the way, guys, whenever you're writing problems, try to have a sequence of steps and put equals. Don't just move to the next line without an equal sign. It feels like, I don't know, like you're leaving it hanging there. Like, oh, so what is that? I don't know. It's something. It's kind of nice to be able to follow your work. If for anything else, to give you partial credit, I mean, I don't know. It's kind of useful. So anyways, the square root of 14 plus square root of 14 is just 2 times the square root of 14, and then that gives us our limit. Now, do I like for you to do rational denominators? No, I don't care. But if you're not in my class and you're just watching this video because you stumbled upon it on YouTube, firstly, thank you. And secondly, ask your professor whether they want you to rationalize or not. All right, this video is getting a little bit long. I think I'm going to cut it here and I'm going to do a part 2 after this. All right, so till next video, guys, thank you for watching and I'll see you in the next one.